So we have our general solutions for the SL problem, which is also a homogeneous solution. It's a combination of the independent, linear independent solution cosine lambda root square x plus C2 sine root square of lambda x. And then we have the boundary conditions, which is y0 equals to 0. That means when you have x equals to 0, right? So y0 will be equals to C1. When x equals to 0, cosine 1 will be equals to 1. So it's C1 plus C2 times 0, because sine 0 equals to 0. That means equals to C1. And because y0 equals to 0, so C1 equals to 0. Then we have YL as well. So YL is the second boundary conditions. YL equals to 0. That leads to our x equals to L. And because C1 equals to 0, so this part will be equals to 0 anyways. Then YL will be only have the C2 part, which is C2 sine root square of lambda L. And this is equals to 0. Then what kind of sine part can lead to overall is 0. Here we need to note also that since our C1 equals to 0, then the C2 couldn't be 0. Then if the C2 is also equals to 0, that will lead to a 0 solution, right? The y equals to 0. So the C2 is now 0. That means our sine part has to be 0 anyways, has to be 0. And you will have the lambda. In order to let the sine lambda L equals to 0, the lambda L root square will be equals to n pi. So that this sine n pi will be always equals to 0, where this n starts with 1, 2, 3 until infinity. So lambda in the end will be n squared pi squared divided by L. So only when the lambda L equals to n pi, this makes sense because you have basically all the 0 points passing by pi, 1 pi, 2 pi, 3 pi, 4 pi, etc. Right? So this is 0, this is x direction, this is y direction. So only when this root of lambda L equals to n pi, this whole term can be equals to 0, right? And this leads to y is not 0 solution. Where uy is equals to sine C2 sine n pi over L, right? So that is C2 n pi over Lx. Okay, so that is your solutions. Then have to remember that our solution is based on an assumption before. The assumption is that my alpha is a positive number, right? How about the lambda is a positive number. How about my lambda is equals to 0? So when lambda is equals to 0, y will be equals to C1 x plus C2. That is based on your R equals to 0. Then you lead to this solution. And if you have the boundary solution, y0 equals to 0, yl equals to 0, then both C1 and C2 will be 0. That will lead to a 0 solution. So y equals to 0. When your lambda is smaller than 0, then you lead to the final solution, which is C1 times e to the negative lambda x plus C2 e to the minus lambda x plus C2 times e to the minus lambda root square x. And when you have y and y0 equals to 0, then this also leads to a zero solution where C1 and C2 is equals to 0. So zero solution. So that's only when your lambda equals to a positive number, then that makes sense, where the lambda equals n squared pi squared over L. That makes sense because you have a non-zero solution of y, and you have unlimited solution of your eigenvalues as well as the unique eigenvectors associated with each eigenvalues. Okay. Then the as a summary of our this problem set, you have the eigenvalue where the lambda is over 0, that lambda n will be equals to n pi over L. N squared pi squared over L squared. Right. So n squared pi squared over L squared, where the n equals to 1, 2, 3 until infinity. And your eigenfunction, so basically your yn will be equals to sine n pi over Lx, where you n is equals to 1, 2, 3 until infinity. And you can try several examples by yourself using different boundary sites. For example, let's make an example 2. You can try from your own. I just gave you the solution here, okay? The example 2. Instead of giving you the direct boundary conditions, which is y0 equals to 0, y equals to 0, you can have Newman boundary conditions, which is the boundary condition only as function of y prime, so that you can try the same problem, which negative y double prime equals to lambda y, with y naught equals to 0, yl naught prime equals to 0. And this is definitely a SL problem because you're basically alpha 2 and beta 2 is not equals to 0. Alpha 1 and beta 1 for the boundary condition equals to 0. So this is still homogeneous boundary conditions with the Sturm-Liouville problem format. And this eigenvalues is lambda n equals n pi over L squared, and start with 0, 1, 2 until infinity. And the eigenfunction is yn of x cosine n pi x over L. So you can try whether you can solve the eigenvalue and the eigenfunctions and using this Newman boundary conditions.